Record test 1, Recop 3 ODS Open Office Calc. We're moving the mouse. The chapter is titled Doing It with Differences. A good bit of Newton and Pascal is referenced. Importantly, as page 10 illustrates, a polynomial takes an input range and generates an output range whose members are pairwise iteratively differenced until a constant across the range is generated. This workbook does difference polynomials, though, as a demonstration of what a Java library is tasked to accomplish. And note, triangle superscript I represents the ith iterated difference. So, P is defined as a set of scalars for a range of values defined by P. Set of iterated differences is drawn out. Triangle 1, triangle 2. P is transformed by adding or subtracting a value to individual scalars. The transform motivation is setting a 0 to an individual range value of P at a particular difference. The scalar degree determines which difference or differences are affected. As in, a change in the 0 degree term of P does not affect any difference, only the function value itself. The first degree term only affects the first difference, the second degree term affects both the first and the second difference, triangle 1 and triangle 2. The third, the first three differences, etc. Note, though, want to affect the highest degree term first, as it fixes the last difference. Triangles of last, and subsequent scalar changes will not affect differences of scalars of higher degree. With x to the fourth and looking at x equals 0, have at triangle 3 36, and want P transformed into P prime equals x to the fourth plus bx to the third with at x equals 0, triangle 3 equals 0. B is the value to adjust P's third degree term, which currently is 0. Solving for B involves using the function minus f of x at triangle I divided by I factorial as 36 divided by 3 factorial equals 36 divided by 6 equals minus 6. Therefore, p prime equals x to the fourth minus 6x to the third, and has at f of 0, triangle 3, a value 0. Next up is an adjustment to the second degree term. P is 0 at triangle 2 is minus 22. With minus 22 divided by 2 factorial equals minus 11, add 11 to scalar 0 for x squared, and p prime prime is x to the fourth minus 6x to the third plus 11x squared. Now adjust the first degree scalar, currently 0, as p prime prime 0 at triangle 1 equals 6, as minus 6 divided by 1 factorial equals minus 6, p prime 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 equals x to the fourth minus 6x to the third plus 11x squared minus 6x. P does have roots at 0, 1, 2, and 3. Note P1, the P described in triangle 1, has roots at 0, 1, 2, and P2, the P describing triangle 2, has roots at 0, 1, etc. Each difference, triangle, triangle I, in the set of differences is described as an individual P. For instance, each triangle I can be transcribed to an appropriate Vander mode and solved with Gauss elimination. There are several ways. Difference polynomials.ods can define the triangle P's. Have a copy of P's differences from prior worksheets starting with triangle 1, and want to fit the differences from high degree to low. Starting with fitting constant equals 24, have third degree term equals 4. Likewise, the second degree term is fitted with minus 12 as the scalar. Finally, the linear term is fitted with 8 as the scalar. Thus, 4x to the third minus 12x squared plus 8 is P describing triangle 1 of P equals x to the fourth minus 6x to the third plus 11x squared minus 6x. As mentioned earlier, the workbook does difference polynomials as a demonstration of what a Java library is tasked to accomplish. The library actually generates and subsequently writes to Neo4j for graphing sets of difference polynomials rooted with the constant term. A feature of this graph is a label for each node interpreting the root set as a rational number. See link on project page for details. This graph is rooted with the constant term 6. A traditional traversal would include nodes with the same denominator. An in-order traversal could emulate rational arithmetic. For instance, the ordered traversal for denominator equals 8 and arithmetic of 1/8 plus 3/8 would imply the fourth node of the traversal would be a polynomial with roots that would encode 4/8. More so, as this graph is rather manageable in size, the graph generated for non-trivial parameters is substantially larger. Leveraging the Neo4j graph data science library, and particularly GraphSage for label inference, structure inference, etc., may reveal efficiencies of scale. So, some structure. And the node set, hang on. A polynomial with no roots. Polynomial representing 1/3. The roots represent 1/3. Polynomial whose roots represent 4/5, etc. And the graph that would be traversed.